You might remember in our last unit on binomial probability distributions that was a discrete distribution. And by discrete, we mean, the value of x, the random variable, could take on only a countable number of values. So we actually had this picture. I just brought it over here. So what we were doing was taking this one unit of probability, right, a square of length 1, 1. If you take a look at the area is 1. So we take this one unit of probability and then we divide it up and distribute it to the values of the random variable. So that's called a probability distribution, right? So this much will go to 0. So the probability of getting 0 would be this much. The probability of getting a 1 would be this much. The probability of getting a 2 would be that much right there. All right, that's for a discrete probability distribution. So now we're going to move on and go to continuous probability distributions. Now, continuous means this. Instead of having countable number of values like 0, 1, 2, 3, 4, 5 successes, we're now going to have an entire interval of values. Like we could go anywhere in the interval from 0 to 5. Like it could be time. Like time could go anywhere from 0 minutes to 5 minutes. So we're going to take a look at that now. We're here in a new chapter, the normal distribution. And oftentimes when we start something brand new, before we start just solving problems, we have to talk about the meaning of everything so we have a good understanding of what it is that we're doing. So when we come across a problem, we'll know that, oh, here's something I can use, and then we'll see how to use it. So there's going to be a little bit of talking or reading up front here, just to warn you. Well, I shouldn't say warn you. I should say just to let you know. Warning sounds kind of ominous. All right, so instead of like a binomial distribution that was discrete, now we're going to take a look at continuous distributions. So let's read through here as best we can. So associated now with continuous random variables like time or weight or height, something like that. So associated with continuous random variables are what's called probability density functions. Now, I'll try to get you a feel for density functions in just a couple minutes. But instead of calling a probability distribution, now we're going to call it a probability density function. So imagine that 1 unit square that we used in that last section on binomial probability. Here's that 1 unit square. And what we did, remember, we divided it up. So we cut it up according to some rule, like the binomial probability function. Divided it up and sent it to the values of the random variable. Well, now, so now imagine the 1 unit square of probability not being cut up into individual pieces, as we did for that discrete variable, but rather stretched and pulled and reshaped into a new form and placed on and above the number line. So we're going to take this square and pull it and stretch it and just shape it into a new shape, like maybe this shape right here, or any other shape, all right? So we're going to pull it and shape it and put it on a number line, okay? And then we're actually going to put it on a coordinate system. So we're going to start things at 0. I'm going to take this thing over here, pull it and stretch it. I still have 1 unit of probability. I'm going to pull it and stretch it to a new shape, and then I'm going to put that thing on a coordinate system. Here's x, and x will be the values of the random variable, but it'll be continuous now, like maybe as time goes from 3 minutes to 5 minutes. And then the f of x, this will be our probability, so that'll be p of x. And now for continuous distributions, we don't ask about the probability that the random variable assumes any one specific number. You know, back in binomial probability, we could say, what's the probability that we get 1 success, or 2, or 3, or 4? But now we're not going to do that. Since there are infinitely many numbers on the number line, right, this is continuous, so think about time. Time's continuous quantity. So since there's infinitely many numbers on the number line, the probability that any one particular number occurs is essentially 0. Right? You have one particular number out of infinitely many, the probability that's going to happen is going to be 0. So we ask rather, what is the probability that the random variable assumes a number within a particular interval? Now, here's what we're going to have. So we might have something like, what's the probability that our random variable assumes a value here between A and B? All right, so this region right here, that's going to be the probability that the random variable assumes a value between A and B. Now, just to give you an idea of what we did before, remember we had that 1 unit probability, and maybe we cut up this much area. Say we cut up that much area, and we put that over to x equals 1. Then we take a look at maybe this much area and put that over to x equals 2. But now we're taking this much area and we're saying, okay, that amount of area probability is going to go for x anywhere between A and B. So if it was time, it might be, like 3 minutes to 5 minutes or something. So where are we here? Now, that probability is given by the area bounded by the curve. All right, so there's some curve now, f of x, the interval. So this area is determined by what? Well, it's determined by the interval that you have, and it's bounded by that function. Now, the vertical lines are the endpoints at the interval. So the area that we're dealing with, or the probability, is determined by the interval that you want. So the value of the random variable lies in some interval, and the curve that you're using. Now, the curve depends on what probability distribution you have, and there's different ones, right? We've already looked at the binomial. We're going to look at the normal, the student's t. There's just a group of ones that we're going to look at. Now, mathematically, the area and probability are equivalent. All right, so when you think of area, you want to think probability, or when you think probability, you think area. So the measure of an area is the measure of the probability of an outcome. Measuring areas, can be made using calculus. Well, we may or may not know that, but that's what calculus can do for us. It can measure areas. Now, we're not going to do any calculus here, but we're going to make use of some calculus tables and the calculus that's built into our TI-84s. The TI-84s and the table have done all the calculus for us. All we have to do is look things up. But if you want to compute an area like this, you have to use some calculus. Now, the probability density function pictured down here may help us understand the term density is used. All right, now each of the displayed intervals in the graph is 1 unit in length. All right, so here's a graph. I've got a 1 unit length interval here and a 1 unit length interval here. Now, the leftmost interval, as you can see, the leftmost interval has more area associated with it than does the right interval, right? There's more area here than over here. That is, this leftmost interval has more probability associated with it than does the right-hand interval. So the probability that x would be in this interval has this probability, that area. The probability that x is in this interval is this number right here. So this one is more likely, right? More probability, more area than this one. And we're going to say the leftmost interval is more dense with probability than is the rightmost interval. Now, I think I can do more with this idea of density. Now, to get a better feel for this idea of density, imagine you have 2 bars of music. Say we've got this bar and this bar. Now, this one has many more notes in it than does this one. So you might say that 1 bar of music is more dense than another. And then what we had in that last picture, I'll try to draw it over here. We had this function here, and then we had this interval of length 1 with that much probability. This interval over here, let's make it even smaller. That interval of length 1, but only that much probability. So this bar of music has more notes than this one. So this might be more dense with music. This interval has more probability in it than does this interval. So this is more dense than this. So really this is a density function. We're taking a look at different densities. To continue on down here, the probability that a randomly chosen value of x lies in some interval is the area of the region that lies below the curve and above the interval. So that's this picture down here. Now, don't worry about this for a minute. The probability that a value of x lies in this interval, like maybe 3 minutes to 5 minutes, what's the probability you do something and it takes between 3 and 5 minutes? Okay, well that area measures the probability. So this is the probability that x is between A and B, right? So what's the probability that X lands in between A and B? It's this area right here. Now what we're saying is this. The probability that a randomly chosen value of X lies in some interval AB is the area of the region that lies below the curve, right, below the curve, and above the interval. Now this figure shows exactly that. Okay, now what I'm saying is this. This area we know is the value of the definite interval. So here's what this is. Now, if you take a calculus course, you may see this. This would appear in Calculus 3, the third semester of calculus, but there's a name for this curve here. We can call it this. All right, here's how you would find that area. This is a calculus operation. This is called an integral. Okay, and it just says find the area. This is what you would do to compute the area of a curve. All right, now we are not going to do that. This is what would take place in a calculus course, but we're going to use all the results of this and put it into tables and built into our calculator.